I visited the East Coast this past winter, and I was greeted by a sight similar to this. We can all relate to the severe snowstorms that affected the US in January and February. Coming back, my flight was delayed a whole day. But I mean, when it's going to snow, it's going to snow, fine. What stood out was this. In places like Philadelphia, New Jersey, and New York City, a potentially historic snowstorm was predicted. But just a few days later, after policymakers had already acted accordingly, only a few inches fell. The bottom line is that even our best weather forecast models have a lot of room for improvement. In particular, I'm sure most of you, if not all of you, have heard the term polar vortex all over the news. Polar vortex, polar vortex, polar vortex. What exactly is the polar vortex, and why do we even care about it? The polar vortex is a large-scale cyclone that forms over the poles of the Earth during wintertime. As winter approaches, the air above the pole becomes a lot colder than the air around it. This creates something called a pressure gradient, which causes air to start flowing inward towards the pole. This, combined with the Coriolis effect, causes the air to turn and start rotating, eventually forming a cyclone. The interesting part about this is that the wind speed at the edge of the vortex can reach up to 80 meters per second. That's 180 miles per hour, about the speed of a small plane. This means that all the cold air during wintertime is trapped inside and warmer air can't get in. So as winter passes, the air inside becomes increasingly cold. So with the coming of spring, the polar vortex will eventually collapse. And when it does, all this cold air that was trapped inside comes rushing down to lower latitudes, like North America. And that's why we get these severe weather patterns. A particularly relevant aspect of the polar vortex is called polar vortex weakening, or PVW. Polar vortex weakening is an atmospheric anomaly that occurs before this final warming and before the final collapse during the months of December, January, or February. And it's when the polar vortex weakens suddenly and dramatically. Unfortunately, the ultimate cause of the polar vortex is still a mystery. No one knows what triggers it. I was curious. If we know so much about the polar vortex, why are the weather measurements so off? I've always been interested in math and science, so I decided I wanted to investigate this issue of the polar vortex weakening and conduct some of my own research. At first, I was very reluctant because the polar vortex is obviously very well studied, and in the past, scientists have come up with some theories regarding why it happens, but they've never been able to find strong enough empirical evidence. Experts have never been able to find strong correlations in observed data, and I was just a high school student finishing up his last few years. Luckily, I had the opportunity to work as a research intern at the University of Colorado at Boulder. And with my new environment and my new resources, I dove into my project. First off, what exactly do I mean when I say the polar vortex weakens? To give you a better idea of what's actually happening, this plot shows the year 1985. In fact, it shows how two things change over time. One, the blue curve is the wind speed at the edge of the vortex, and the black curve is the temperature in the center of the vortex. So you can see on the day of the polar vortex weakening, which is indicated by the vertical red bar, the blue curve dips suddenly. And at the exact same time, there's an upward spike in the black curve. This is because as the blue curve, which is the wind speed, as it slows down on the edge, some warm air is allowed to get in. And this, in turn, warms up the center of the vortex. So this is a very, very prevalent trend right here, as you can see. There's the two peaks that happen simultaneously. And this phenomenon is known as the polar vortex weakening. In a lot of atmospheric science, the focus is on the sun, because it is such a big part of everything that goes on Earth. But in the course of my project, I realized that the stratosphere, which is the layer of the atmosphere where the polar vortex is, the stratosphere and up only absorb 1% of total solar irradiance. In other words, there must be some significant energy source coming up from down below. This led me to think about oceans. Another main detail that really reinforced this idea is that, of course, in the South Pole, there's also a polar vortex. But it doesn't display any of these weakening effects, and it doesn't have PVW at all. Obviously, the biggest difference between the North Pole and the South Pole is that there's no ocean in the South Pole. So this really narrowed down my thought process to two main things. One, the Atlantic Ocean, and the other one, the Pacific Ocean. In the Atlantic Ocean, there is a major warm water current called the North Atlantic Current that flows up into the Arctic Circle from between Greenland and Scandinavia. It's part of the Gulf Stream. In the Pacific Ocean, there's also an opening into the Arctic Circle between Alaska and Russia. I'm sure many of you are familiar with it. It's called the Bering Strait. But it's much more narrow, and there's really no significant current flowing up through there. So in the end, my idea was that the North Atlantic Current carries warm energy, heat energy, into the Arctic Circle. This energy eventually propagates up, and that's what weakens the vortex. So this was the hypothesis that really drove my project. The hard part about all this is quantifying something as large as the North Atlantic Current and correlating it with both the timing and the strength of the polar vortex weakening. I was sifting through a lot of really raw satellite data that just were a bunch of numbers, incomprehensible, hard to read, and trying to look for patterns and trying to find evidence for my hypothesis. After several months and a lot of trial and error, trying different procedures, trying different variables to represent the heat energy, trying different regions of the ocean to indicate the current, I was able to get a 99.95% level correlation between the weakening and the current. This is an example of the actual fit. On the x-axis, we have the actual OAT, or ocean air temperature. That's the variable I ended up using to represent the heat energy that's there. On the y-axis, I actually have the occurrence, or the timing, of the polar vortex weakening. It's measured by DOY, which is day of year. And the positive numbers just count forward from January 1st, and the negative numbers count back into December of the previous year. Every point on this plot represents 1 year. So you can see I have about 30 years included in this plot. For those of you familiar with statistics, this line is called the linear least squares regression trend line, and the correlation coefficient is 0.76. Essentially, the closer this value is to 1, the stronger my fit is. So this is very strong. In other words, it means that there's only a 0.05% probability that these results occurred by chance, or from randomness. Think about that. In other words, I was able to find a very, very strong correlation between two seemingly unrelated entities. One, an ocean current, and two, this giant thing in the atmosphere. So this has several implications. The first being that it's really strong support and very powerful support for my original hypothesis that the North Atlantic Current is indeed what's causing this polar vortex weakening. Establishing this relationship between the ocean and the atmosphere is the key to improving meteorological weather forecasts in the future. The results for my project, this project in particular, can be included in existing models to improve their accuracy, so that in the coming years, we will know exactly when the polar vortex weakening will happen and just how strong it will be. Looking back, I couldn't have done any of this if I just stayed in my comfort zone and believed I couldn't have gotten any results. I thought scientific research was reserved for expert professors who had years of experience and had written a lot of papers. But I was lucky enough and fortunate enough to actively go out and seek my own research internship at CU Boulder to pursue my ideas. I urge everyone here to actively go out and try something you've never tried before and try to learn something you thought was impossible. I thought TEDx talks were reserved for extremely experienced speakers, but I just did one. And I'm very happy that I did. Thank you all for listening.